EU, and this is my Lab 3. Introduction. So in this lab, the main focus was on the calculation and the observation of magnetic fields and their directions and how distance affects the magnitudes of these magnetic fields, called distance dependence. We also compared on and off axis fields, and we used the Biot-Savart law to calculate the distance dependence for both on and off axis fields. We also had to compensate for the Earth's magnetic field, making sure the magnetic field of the bar magnet was orthogonal to the Earth, so we didn't have any unwanted effect from the Earth's magnetic field on our results. The ingredients needed for this lab were a bar magnet, magnetometer tape, an app, some tape, a meter stick, and a ruler. So the data. I used a Teslameter app on my phone to find the distance for certain x component magnitude values, and also for the off-axis magnitude parts of this lab. Used the Teslameter app. And as you can see on the graph on the right, this is only from the on-axis measurements. This graph measures the ln of bx over the ln of r. And this graph allows us to derive the value of the n value and also to get the y-intercept, or otherwise the ln k value. So my n value was negative 3.5592, which is pretty good because it was pretty close to negative 3, which is what we wanted. And I had a y-intercept of negative 15.334. And so setting this to be my ln k value, I used the equation k equals mu naught times mu over 4 pi to find a mu value. And the mu value that I calculated was 2.19. So for the code. I used the formula given above, which was given in the lab instructions to computationally create a function for B, or for the calculation of the magnetic field. And this was also used for the calculation of the axes for each of the arrows representing the magnetic fields, as can be seen in the output on the right. Looking at the output on the right, the orange arrows represents the on-axis magnetic fields pointing to the right, and the blue arrows represent the perpendicular magnetic fields. And as you can see, as they're perpendicular, they would point in the opposite direction. The pink arrow represents the 45-degree off-axis magnetic field, and as you can see, it's very, very close to my magnet, and that was what I got in my lab results. For the 45-degree off-axis field, my D-perp was very, very small, and as you can see on the output on the right, for the values that my computational model outputted, the D was very similar to what I had gotten. So questions. What if you hadn't oriented your experiment to compensate for magnetic north, and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, it would have changed a lot, as the Earth's magnetic field would have altered the experimental results, as it would have altered the direction of the magnetic field, as in when we were trying to get it as close to zero as possible. That was so that we purposely took out the effect of the Earth's magnetic field. We made sure that it was orthogonal to the Earth's magnetic field. If we hadn't, then it would have skewed all of our results, and therefore all of our other calculations. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? Well, I would just expect the magnitude of the magnetic field or the strength of the magnetic field to double, as you're just dealing with two magnets instead of one. And that's it.